Dr. M. Subbiah is an assistant professor in mathematics in LN Government College, Poneri. He has specialized on statistics interdisciplinary. Being interested in active research program and mathematical or statistical modeling, he has knowledge in operating various softwares on statistical tools and on technical computing. Having 16 years of teaching experience, he has published papers in 8 national and international journals, and has also presented papers in 10 national and international conferences.
Welcome to the UGC lecture series on mathematical sciences. In this discussion, we will see the two methods in fact for parametric inference in the topic of statistical inference theory. So, first of all, let us quickly understand the idea behind the parametric inference, or particularly the point estimation. Then we will find out through some simple examples how the derivative test, the second derivative test, will be useful through the method called maximum likelihood estimator, as well as one of the simplest techniques in statistical inference, method of moments. So, two methods we are likely to discuss to understand the point estimation in a very simple and fundamental way. So, the two type of estimator we are likely to discuss, as I mentioned. So, the words are quite direct. So, here we are likely to use the moments, and we try to maximize using an idea. That is what I mentioned, using the calculus approach, and through few examples, but standard and important examples, we try to understand these two methods in this particular discussion. The method of moments is something deals with the moments of sample and population. Hence, first we try to recall or understand the main difference between population and sample. The idea of this entire statistical inference is to know about some unknown constant which are random in nature, which will give which acts as a characteristic of the population under study. For example, mean waiting time of a passenger in a bus station. So, the population would be, if it is a metro city or anywhere, we take that the people who will use that particular route and wait in a particular bus stop, which we are trying to understand or investigate. But it is nearly impossible to understand or collect all the information pertaining to the population, because that is also very much random. So, we try to, or we intend to do some sample, though this discussion is not involving with the ideas of sampling. The process of sampling is inevitable, important, sometime which has to be done, compulsory, mandatory. Therefore, the idea of sample comes from this investigation about a parameter. So, the word parameter in this discussion relates to an unknown constant, random constant, which is a characteristic which may be a single value, or it may be multivariate, more than 2. Therefore, we need to understand the terminology number 1, parameter, and then population. Then to study or to investigate the idea about this parameter, we try to take sample. Now, let us look back to our definition. The moments can be calculated for two aspects. One is for sample and another one is for population. So, in what way? Let us take this terminology in a mathematical form. An event of uncertainty, that is what I say, which randomness involved, is assumed to follow a distribution. So, this is a data part, and this is the symbol is given as theta which is for the parameter. So, as I mentioned, it can be a single or k parameters altogether. So, we try to calculate the first k moments of sample and population. Then we try to match them. Symbolically, we try to fix ourselves that we have k parameters altogether, and the symbols m stands for, or mr stands for the rth moment about the 0 for the samples. Same thing can be calculated for the population also, so that it is distinguished in the symbol mu r dash. Now, what we try to do is we try to compare mr, that is the moment about origin for the sample, and that of population. So, that is the simple mathematical expression we could say, but sometime computing these moments will take the real task, and moreover it is the understanding of the distribution. So, in the previous slide we observed the distribution follows a parametric form f of x given theta. So, this format is very important. So, once again in this discussion we are not completely confined to the idea of how to fix a distribution. So, we assume that some distributions are known and we are able to distinguish in the distributional form two things. Number one, which is data part, invariably x and y refer to those, and theta, which is also a standard uniform symbol throughout the literature, where theta refers to a single or a set of parameters. So, with that understanding and assumption, we try to look at some simple examples, so that we are ignoring two things here. Number one, the various aspect regarding the sample. So, that is not been covered here because this is not the course regarding sampling theory. So, this is only an inference. So, assuming that we know something about the sampling process and we have some sample data, which we call them as x1, x2, etc., xn. So, without saying, n stands for the sample size, and another symbol we refer here is we refer k as the number of parameters. In the beginning we try to do with k equal to 1. That means only one parameter, and simple known models will be considered like binomial, Poisson, or normal, or beta. So, these kind of distribution assumptions are also essential to understand these examples. That is what two things I told you. One is regarding the methodology or the methods of sampling, another one is the distribution theory. So, in distribution theory we are exposed to understand why there are many parametric distributions and how a data model is assumed, or it can be linked to an underlying parametric distribution also. So, in that idea there are very fundamental distributions which I am going to deal now for illustrating the method of moments. Therefore, the examples might straight away start with the distributions. Let us try to start with the simple Bernoulli's form. So, the Bernoulli's form is something like an binary outcome. So, though I am not talking more details about the distribution, a slight introduction about or recall about the distribution, and this theta is value lies between 0 and 1. So, it is binary like a yes or no or present absent, something like that. So, it took value for two aspects where x is that. So, its PDF is a simpler form. We have theta power x and 1 minus theta power 1 minus x. So, if you calculate the sample moment, let us say m1. So, here what we refer as k, number of parameters, will be equal to 1. So, we will be calculating only one moment, which is the sample moment, and of course, it is always xi by n summation of, which is nothing but x bar. So, this will not change. However, if you take mu 1 dash, which is expectation of x in this case, which is simply theta. So, what we are supposed to do in MOM is simple. We try to compare these two, compare theta and x bar, and you call that as method of moment, and the estimated value is normally represented over hat, and I prefer to write which method we are following, method of moments, so which is x bar. So this is a simple case. So what we need to know for in each case is, from this example we could find out that first thing is f of x given theta, that form is essential. Then how many parameters it has, as many times we calculate the moments of our sample, and here it is for population. So that is the difference. So the symbol is slightly makes the understanding clear. Xi, so here I assume that there are n samples being collected, we are comparing. So this simple example illustrates how it is being worked out. When you try to extend this particular form, you can go for binomial distribution and try that particular part. But before that, we try to do one more example. Let me select from Poisson case of again theta. So usually in mathematical statistics it may be lambda, but deliberately I take theta to hold the meaning of parameter which we started earlier. So quickly we get into its PDF, e power minus theta, theta power x divided by x factorial. So once again I confirm that my number of parameter will be k equal to 1. So once again I quickly calculate m1, which is as before x bar, and here mu 1 dash, which is nothing but expectation of x. In this case again it is theta, so comparing we will get theta hat of mom, that is method of moment is x bar. So somehow both examples have very similar answers, but not necessarily. So these examples are only to illustrate what are all the significant steps involved, and then what to calculate, and then finally what to do with the method of moments. Let me take another distribution from a continuous family. X follows uniform of, so I will write little more details. Say I can have theta comma 2 theta. So without explaining, this theta is a parameter, only one parameter, so k equal to 1. So if you look at this PDF here, we have 1 by b minus a, so 1 by 2 theta minus theta, or it is 1 by theta as far as x is varying from theta to 2 theta and 0 elsewhere. Anyway, our first moment, namely m1, still stands with x bar, and here if I calculate mu 1 dash, as I told you, I assume the distribution theory. For uniform distribution we have the mean, okay, first moment, namely expectation of x, as I can recall a plus b by 2, where a is the lower limit and b is the upper limit. Therefore here in this case theta plus 2 theta is 3 theta by 2. I am comparing these two things, x bar equal to 3 theta by 2, and that makes the calculation straight away theta hat equal to 2 x bar by 3 or 2 by 3 x bar. So for understanding I write MOM. Once again this example also becomes a simple multiple of x bar. So all the three examples are invariably dealing with the sample mean. If I look at the three constants what we estimated here for the three examples, okay, it's not mere coincidence. Invariably the sample mean comes to in the particular part, because we are trying to compare the first moment, which is nothing but the sample mean. So it is not very surprising or very much unusual. So directly we are comparing and then try to find out the original, I mean the parameter moment of order for 1, then we try to compare. Therefore you can understand the first moment alone if we consider, then it will be naturally some function of x bar, namely sample mean. So that is what we try to understand. We are looking at the sample moment, and then other side we are comparing the population moment, and all these things are dependent on how many parameters we try to have. In the case of two parameters, let us take the simple example again. Simple or simplicity, all I mean to say here is the background knowledge of the distributions. So, normal of mu comma sigma square. So, n here refer to normal distribution. So, if I write the distribution here, so I assume that theta is mu and sigma square, both are together. So, I have k is 2, that is all. So, quickly we can write, though we may not require very straight to calculate, let us try to recall what is being done. So, x minus mu the whole square divided by 2 sigma square. So, there are variations on mu and sigma square and x also, which varying from minus infinity plus infinity. So, now we have a case for k equal to 2. First of all, I calculate m1 as x bar. So, xi by n. Secondly, I calculate m2 using the same idea, second moment, and here the mean, that is mu 1 dash, is expectation of x, which is nothing but mu. Mu 2 dash, we have to calculate mu 2 dash for the population, which is expectation of x square. So, I am not going to calculate here. Once again, I will be using the results which we know already. For normal distribution, actually variance of x is sigma square. By formula for variance of x, it is e of x square minus e of x the whole square equal to sigma square. So, from this I need e of x square. So, I can plug the value of e of x whole square. So, ultimately from this relation I am borrowing. So, e of x square equal to variance of x, namely sigma square, then this plus we have mu square, that means e of x the whole square, which is nothing but mu square. So, I am comparing this constant. Now, what we try to do, we have two moments in this side, two moments in this side, and we try to compare those two things. If we compare it directly, we have mu is equal to x bar. But remember, our theta is two items, therefore, I avoid theta hat straight away here. I am trying to estimate these two parameters using these two constants or these two moments above in the sample. Anyway, the first item in my parameter is being estimated, therefore, I can say mu hat of MOM is x bar. So, job is done. Let us take this again case. These two has to be compared. So, sigma xi square by n will be equal to sigma square plus mu square. So, mu hat square or x bar square. This is going to be sigma square is equal to, still I write the same form sigma square, though we are trying to estimate it, sigma xi square minus x bar the square. So, this illustration is to handle the case for k equal to 2, and I am using the same idea, first two moments and second moments are compared, thereby we are getting this answer. So, this can be written with the simple algebra, x bar is sigma xi whole square by n. So, I can write it as xi minus x bar the whole square by n. So, this form will be taken as sigma square or sigma square hat of MOM. Therefore, the two the last example illustrates how the method of moment can be extended to more than one parameter case. So, the process has to be continued as many times you have the parameters. Okay. So, for example, if I have a binomial distribution, the problem can be phrased as only theta is a parameter. Suppose if I compare, or if I want to study that n, that means the number of trials, as well as theta, that means the proportion of success, both are unknown in certain cases, then the same problem become the inference about two parameters, n, namely number of samples or repetition, and then theta, proportion of success. So, these kind of problems can be devised based on the situation. That is where the number of parameters are also fixed, and hence the number of moments to be calculated on sample and population both are fixed by the definition of the problem. Underlying fact is calculate the moments and then compare to identify the estimators for the parameters. Okay. So, that is all about method of moments. Now, we shall quickly move into the second topic of our today discussion, the maximum likelihood estimator. So, again we are having the same terminology, therefore, I will go into quick. There are n items which we call it as a sample, and which is collected from a population which follows probability distribution. A word here we try to use which we call it as likelihood, therefore, the word L stands for that. So, here I just want to spend a few minutes here that both are exactly same. So, we use the word PDF, probability density function, or a distribution f of x given theta. Now, it is slightly rephrased as likelihood function of theta. So, the orientation is slightly different, or importantly it is different. The first one, which we call it as probability density function of x given theta. So, once you know the value of theta, or estimated, or whatever the other ways to understand the parameter, we can calculate or we can understand the probabilities based on x, that is data part. Now, if you look at L of theta given x, the same function is oriented in a different manner. If I know this data, I have a sample here, what can I say about the likelihood or the plausibility of theta? So, here I calculate the probability for x related when theta is given. The same thing is rephrased, the plausibility of theta and when the sample is given to you, or when you know something about the data. So, this is based on some idea called identical independent distributions. So, independent helps you to multiply the joint probability event. So, f of x I given theta. So, this step comes from once again mathematical statistics under the definition or the assumption of independence. Then theta we are making it a fixed parameter for the unknown parameter, therefore, it is identical over the entire distribution. So, f of x I given theta in the product form is resulting from the basic assumption of identical and independent distribution. Usually, we abbreviate it as IID. Therefore, L of theta given x is a word we try to use to understand that we are trying to estimate theta or looking out the plausibility of theta under the light of data. That means, given data, what I can have, what could be the most plausible values of theta. Therefore, it is not probability, it is something about the plausible value of theta. So, that is about the symbol, because we have to comfortable with the symbols also. In this case, before I go into an example, I just want to talk about one more notation which I deliberately avoided in the earlier slide. Here I make it L of theta given x more detail in the previous slide. Now, I will be taking one more symbol from this using a known transformation, natural logarithm. So, we will take logarithm and a symbol small l of theta given x will be followed in many texts. Sometime it may be interchangeably, but here we try to understand L of theta given x in the original form and small l of theta given x will be in the transformed form. The transformation will be natural logarithm of the given function. So, if I take the binomial case for example, which we have not done in the previous form. So, ID, as I mentioned you, the form binomial of n comma theta, only one parameter. Of course, here we do not mean much about that, but anyway we look at what will happen if I have more than one parameter. The simple idea is, so if I have capital L of theta given x, I have, after getting the Bernoulli's form, we have NC x, so in the product form, theta power xi 1 minus theta power 1 minus xi. So, ultimately we have theta power sigma xi 1 minus theta power n minus sigma xi. So, I may simply write it as theta power x into 1 minus theta power n minus x. So, what is my x? It is sigma xi. So, for simplicity I just rearrange the term. Then if I take L of the same function theta given x, I have natural logarithm of L of theta given x, which is natural logarithm of theta power x into 1 minus theta power n minus x. So, I apply log rule, x times log theta plus n minus x times log 1 minus theta. So, what this likelihood function will say? Maximize likelihood function. Let us recall the title, maximizing the likelihood function. We got it. So, I will apply the calculus approach. Dou L by dou theta will be x times 1 by theta plus n minus x times 1 by 1 minus theta. Applying the chain rule, we have minus 1. So, x by theta minus of n minus x times 1 minus theta. So, the calculus approach requires this part has to be made 0. So, when I take dou L by dou theta equal to 0, then what we try to do is x by theta minus n minus x by 1 minus theta become 0. So, if I take LCMs, x into 1 minus theta minus n minus x times theta become 0. So, if I take theta as my factor, then this, if you take x minus theta, x theta we have. So, n minus of, and what else you have? This x theta will be cancelled out and you have minus x. So, theta hat equal to x by n. So, once again you come back to our main problem. We are equating it this equal to 0 for the calculus approach. I want to maximizing. So, dou L by dou theta become 0 and we have theta hat equal to x by n. Remember what is x, which is summation of xi by n, and once again we end with x bar. Nothing more surprise about this discussion that most of the problems are ending with the estimator of sample mean. We are more often using that particular cases and these examples are going towards that particular estimator, namely sample mean. But for that the examples are to illustrate how the method being used to get the values of the point estimator in a one parameter family or a 2 parameter family. So, the first procedure compared to second, which is much more easier, but not always, because in some cases the methods, calculation of method or method may not exist for certain cases. Therefore, this may not compare which way we are trying to use or when to use, but both are available. It depends on what kind of problem and what kind of methods we have to calculate, to estimate the or to find the point estimator for the parameters. So, these examples illustrate two important, most oftenly widely used techniques in statistical inference called method of moments and maximum or maximizing likelihood function, ML Few examples following this will help you to understand to find the process. So, one is to calculate the moments, that also important, and again second one is a calculus based approach. Therefore, knowledge of calculus and equating to a first order derivative to 0 to find the critical points, which are all the basic prerequisite to find out an estimator using MLE. In summarizing these cases, there are few examples following this particular part to work out the ideas of method of moments and once again the maximum likelihood estimator with the prerequisite I told you. Without knowing the calculus part, it might be difficult to maximize, though in certain problem the method also fails. Anyway, these two techniques which are essentially important as far as point estimator is concerned, and following this we have few examples for that. So, these are all based on the standard format, like the beta one I told. Then in normal I suppress one parameter, though it is theta and sigma square which observed in method of moments. Here I deliberately suppress the value of sigma square as 1. Therefore, the family becomes one parameter, namely theta alone. So, that which we make it as theta greater than 0 also. So, what will happen if this additional condition is imposed? So, this discussion is all about introducing the idea and illustrating the concepts of a method of moment and maximum likelihood estimator. Thank you for joining.